Yeah.
Okay.
We don't need it this time, but can we have a clap?
Sure. 3, 2, 1. No, that's terrible. Nobody else claps.
Yeah.
The point is audio sync.
Yeah.
If you all clap, that completely ruins it.
Right back at the end, though.
Yeah.
That's acceptable. That's acceptable. We just won't audio sync at the end. Okay. Well, thank you very much for coming out tonight. So this is going to be a talk. Well, this is the first of 2 talks about the second year linear algebra course, and I'm going to try and do as much as I can to kind of motivate the course, explain the high-level intuitions, and kind of focus on the hardest parts and kind of try and explain them better and help you think about them the right way. And one theme that I think is really important to linear algebra is that it's just really useful in ordered maths. And so I'm going to take a few tangents throughout to talk about how it's useful everywhere else. For example, in the middle of today's talk, I'm going to talk about how it's useful in statistics and doing linear regression problems. Notable for being completely unlike how the second year course teaches linear regression. And in talk 2, which is happening on Monday at 7:30 in here, I'll be talking a bit about numerical analysis methods and how linear algebra is useful there. And one fun thing before I begin, one of the reasons I'm doing this kind of thing is I want to kind of get as good as I can at like speaking and giving talks and teaching. So I'm going to post a feedback form to the Facebook event after this. I'd really appreciate if you could just like say what you thought of this, say anything you think I could do better, say anything you'd be interested in seeing in the second talk, or anything I could change. Or just tell me it's great. I like you guys rating as well. That's great. Cool. So without further ado, I'm going to get into some linear algebra. So the first chapter of this talk, I'm going to call Intuition. And apologies in advance for my handwriting. And this chapter is basically going to be a kind of whirlwind, high-level overview of the entire course, why the course exists, what the point of linear algebra is, and what I think the most important intuitions are, and what the most important results of this course are, and just how to think about everything. So, at its heart, this course is about like studying vector spaces. So things where you can add things and things you can scale. And the second most fundamental object of this course are linear maps. These are maps between vector spaces that preserve addition and preserve scale, which is kind of the only natural function you could ever have on an object, where the interesting things are you can add and scale. And in some sense, the reason we study this is just that this comes up everywhere. For example, if I want to solve a mechanics problem, a really natural setting is like you put things in a plane and you think about the position of an object by its like x and y coordinates, and this is a supernatural setting for this kind of thing, because for example, forces are an object we care about, and the resultant force is just the vector addition of the forces. It comes up all the time in geometry, things like symmetry, for example, rotations, reflections, scaling. These are all just examples of linear maps, and these all live in RTN. This is a vector space. A slightly more interesting example is in calculus. Every time you differentiate, as we've seen in analysis 2, what you're really doing is just approximating a function with a linear map. Like, in one dimension, you have a curve, you draw a tangent line to it. This is really just saying the change of the function near this point is just a straight line, a linear map. Yeah?
Do you have a black pen? It's not picking up very well.
Sorry. Oh well. Does anyone have a black whiteboard pen on them by any chance? Take that as a no. Sorry. Apologies to anyone who's watching this.
It's their fault for not coming.
Yeah, it's their fault. So, yeah. And as I said earlier, I'm going to give a bunch of examples later on of kind of where this comes up elsewhere in maths, especially elsewhere in second year triangles. And kind of on a super high level, this entire course is just studying linear maps in different contexts. Like, if you look through the chapter headings of Dexter's notes, it's just linear maps between V and W, linear maps between V and V, bilinear forms, maps of dual spaces. This is the fundamental object we're studying, and we're just looking at how it appears in different contexts. And here we come to kind of the first high-level idea. The point of this course is that this kind of thing comes up everywhere in maths, and a super fundamental idea of pure maths is you take some ideas that come up everywhere, you just abstract out what these ideas really mean, and you just study these ideas. You kind of build intuition, you build a box of tools, and then whenever you see a case where these ideas apply, any case where you apply linear algebra, you've already got this deep understanding that you can use. This is kind of what algebra as a subject is all about, and linear algebra is just an expression of this for a particularly nice set of rules. So the first question you should ask yourself whenever you're learning a new area of maths is just, what's the point of this? What are the important definitions? Why have we defined them? And the fundamental definition here is vector spaces, things you can add and scale. And I think that the kind of fundamental intuition this captures is the idea of degrees of freedom. Having k things you can vary independently. For example, in the plane, this is a vector space. I can pick any point, and it's just a point. But I could also represent it as an x component and a y component. And these are two things you can vary independently. And in some sense, the reason we come up with a definition of linearity, a black pen. The reason we come up with the definitions, you, sir, are a true mathematician, white pen on you at all times, whichever it is. Yeah, so this is all about degrees of freedom, things you can vary independently. And kind of the point of addition and scaling is that you can take, say, two axes, the x and y axis, or just any set of vectors, and you can describe any point using these, where you could vary the coefficient of this vector and this vector independently. And this is kind of the fundamental intuition of this entire topic. And every time linear algebra comes up elsewhere in maths, you should think to use it because there is this notion of degrees of freedom and things you're varying independently. So to take kind of one example where this comes up, or to take one example of kind of a deeper intuition about degrees of freedom, let's study linear equations. We've got three variables, x, y, and z. They're real numbers. They can all vary independently. This has 3 degrees of freedom. Now, let's imagine I have equations to solve. I add constraints. The first constraint I might add is y minus 0. And this removes 1 degree of freedom, because y is now 0. I can add a second constraint, z equals 0. I've now removed, this is a second constraint, and it's kind of different from the first, so I only have 1 degree of freedom left. But it would also be possible to add constraints that kind of do nothing. This doesn't change anything, because it's exactly implied by the previous two. And so our first important intuition about degrees of freedom is every time we add a constraint, we either remove 1 degree of freedom, or it does absolutely nothing. And the way this is formalized by linear algebra is the rank nullity theorem. This theorem states that whenever you have a linear map, and you look at so this is from a vector space to a vector space, and the rank nullity theorem says the dimension of the initial space, the number of degrees of freedom, is the nullity of f, so the dimension of the kernel, the things that are set to 0, plus the rank, so the dimension of the image. So, and the way to think about this is dimension is just the number of degrees of freedom. And this tells me the number of degrees of freedom I start with, minus the number of independent constraints, the number of things that are set to 0, is the number of degrees of freedom left, the number of things I can vary in the image. And I think the rank nullity theorem is kind of a underrated, incredibly important theorem, because it's what I like to call an intuition pump. It's a theorem that isn't hard to prove, but it takes this fuzzy intuition of degrees of freedom, constraints, independent constraints remove things, and it converts it to a formal thing that I can use and I can apply in problems. And so you always need to use rank nullity every time you think about degrees of freedom and constraints. And the second, another very important thing to highlight about this course and this talk is we're studying finite dimensional vector spaces. So these are things where finitely many degrees of freedom. And kind of the reason we do this is that these are like really easy, and interdimensional things are hard. And the kind of intuition for why these are easy, but still useful, is that they're analogous to finite sets. You can pick a finite set of things, like your basis. You can vary each one independently, and you get lots of results that are kind of analogous to there being this being a finite set. For example, I think the most important one is, I should leave that up, but the most important theorem says F is an isomorphism, i.e. it's an invertible linear map, if and only if two of the following three things are true. F is injective, it sends nothing to zero, you've got trivial kernel. F is surjective, it attains the entire image, and like the dimension of the input and output space are the same. So F is an isomorphism if and only if any two of these three things are true. And what this theorem is basically saying is we're thinking about degrees of freedom, and through the lens of degrees of freedom, V and W are both finite sets. Like, they have finite many degrees of freedom. And a map between two finite sets is a bijection, if and only if any two of the following are true. The function is injective, the function is surjective, or the sets are the same size. Like, an injective function from a set of size n to a set of size n must be a bijection. And this theorem is basically just that. Finiteness is nice because things are like lovely and constrained, and you only need to know two of these three things to get the other one. Another reason I'm highlighting this theorem is the consequence of a rather more exam-focused point. I think that one of the like super useful but underrated exam strategies is to kind of think about the course through the lens of what are the typical questions? Like, what are common words? What are common things you need to prove? And how do I do them? And I think this theorem is super important in that lens, because a very typical question or sub-question is something like, prove F is an isomorphism. And every time you ever see that, you should immediately think, I'm applying this theorem. Which two of these three things is easiest to do? And a lot of the time, that will just make the question like significantly easier, because that's what the point of it is. So yeah, so that's intuition one. Linear algebra, it's all about degrees of freedom, and rank nullity just kind of formalizes the notion of degrees of freedom and how constraints affect it. Intuition two is the idea of a basis. So a basis is just like a set of coordinate axes. It's just like a finite set of things, v1 until vn, so that I can write every vector uniquely as a linear combination of these. And at first glance, it doesn't seem like a super deep or interesting like definition. It just seems like an obvious thing. But I think that in some sense, this is like the heart of linear algebra. The reason we care about bases is that bases let us take this big, messy, abstract notion of an n-dimensional vector space and just break it down into n independently varying numbers. This is just like this is just a really nice way to phrase the fact that there are n degrees of freedom. We just actively choose n things to vary independently, and we give each of them a number. And I'm going to spend quite a while talking about bases because they are so important. And kind of another high-level maths point is that the things you should always pay attention to when you're learning maths, when you're learning a new area, is like, what are the things that are complicated and hard? Abstract vector spaces. And what are the ways to think about them? What are the like ways to make it nice? And the thing that is hard is abstract vector spaces. The thing that is lovely is a basis, because numbers are easy. And so I think there are kind of maybe three kind of lenses to look at linear algebra through, and they all kind of relate to how you think about bases. So the first lens is kind of how vectors and matrices does it. So you've got this single basis, a standard Cartesian basis, and you phrase everything you ever encounter in terms of this. Linear maps are matrices. They're just grids of numbers. Vectors are just like a column of numbers. Everything you ever do is phrased in terms of this basis. And there's some value to this mindset. Like, it's really useful for computation. But I think that this is like a deeply, deeply limiting way of looking at the subject. And I hope nobody here tries to look at it through that. If you do, please rethink your life choices. So the reason I think this is so limiting is that a basis is kind of the lens you look at the space through. And if you just pick like a particular lens and you only think through that, you lose the fact that if you took a different lens, like if you took a different basis, you would still be accessing the same underlying structure. Like when you take a matrix and you conjugate it by another matrix, you change your basis. You're just writing the same matrix. You're writing the same linear map in a different basis. And whenever you phrase things in the VNM way, like you define determinant as this ungodly sum of permutations, you define trace as the sum of diagonal elements, you think of everything as grids of numbers, you're like fundamentally losing so much structure because you're including the way you think about the space in the definition, and you thus lose the fact that there's this underlying basis-free structure. So that gets me on to kind of mindset 2. Think about everything purely in the abstract. Like, don't even engage with bases at all. You look at linear maps as just abstract functions. You study kernels and images, and you kind of have arrows going everywhere. And I think this is also like a really good and useful lens. So I think this is like actually quite a useful lens. Like there are lots of things that emerge nicely from this. You don't have any issues about it not being obvious that things are basis free. But I think that this mindset is limiting because abstract things are really hard to think about, and bases are useful because they let you kind of break it down into something simple. And so the third mindset, and the one that I'm going to try and drive home again and again throughout this talk, is the idea that the basis is the lens you look at your space through. And so you should read your problem, look at the structures you care about. Like, do I care about subspaces? Do I care about particular functions? Do I care about inner products? And choose a basis that works nicely with that. Because the basis of the lens you understand your space through, the thing you want to understand is your problem. So you want to choose a lens which fits that problem well. And from a certain perspective, the entire linear algebra course is just an odyssey about how to choose the right basis in every setting you could ever desire. And that's what I'm going to talk about for the next while. So the first really, really important theorem about choosing bases and how great this can all be is the Steinitz exchange lemma. So, and again, I think that Steinitz is kind of a underrated theorem. Like, you look at it, it doesn't seem incredibly deep, it doesn't seem that interesting, but this is one of the most important theorems in the course. So, the statement of this theorem says, if I have a linearly independent set of size k of vectors, and I've got a spanning set B, then I can remove k vectors from B, add in A, still spanning. So, sorry, if anyone hasn't seen this before, does anyone want me to go through this in any more detail? Because this is a really important theorem. Sorry, raise your hand if you want to see that in a bit more detail. Sure. So, this theorem is saying that, for example, if I started with a set 1, 0, 0, 0, 1, 0, 0, 0, 1, this is a spanning set. I then take, so this is B, I then take a second set A, which is linearly independent. For example, it looks like this. Then I could take these two, remove these two vectors, add in 1, 1, 1 and 1, 1, 2. I could remove this vector, and this is still a span. And the point of the lemma is that I can always do this. So, pretty sure that one is valid. And So this is, I don't really like this phrasing of it. I think the right way to think about Steinitz is that if ever I have a subspace, like I'm looking at the plane and there's a line, I can take any basis of the subspace, for example, a line, and extend it to a basis of the entire space. I could take like a vector on this line, and then there's some other vector I could take off the line, and this gives me a basis for the entire plane. Or if I had like a plane in 3 dimensions, I could take any basis of the plane and then add on a third vector, like say orthogonal plane, and this gives me axes. And the reason this is like such an incredibly important theorem is that this lets us take any problem where we care about subspaces and come up with a basis where the subspaces look nice. For example, over here, I had a plane inside R cubed. I took as an axis of the plane, I added a third axis, and this made it, this basically made it so this plane was the xy plane. And that's just obviously much nicer than having an arbitrary plane. And it gets deeper than that. For example, if I had n nested subspaces, so like a line, a plane, a 3D space, a 4D space, etc., I could choose a basis of this, extend to a basis of this, extend to a basis of this, extend to a basis of this, etc. And then vectors in each subspace look really nice. They're just a bunch of numbers followed by zeros. For example, if the first 2 things were a line and a plane, I can get a basis that looks like this. And this is anytime you ever have a problem where you need to deal with subspaces, you should always use Steinitz to choose a lovely basis to respect the structure. So let's take an example problem. I have 2 subspaces, U and W, like say 2 planes in R cubed that overlap at a line. Then I can define the sum of 2 subspaces as like, you take any vector in one, you add it to any vector in the other, this generates like a new vector space. And then the dimensions look like this. And the reason this is true just immediately follows from taking the right basis. The two subspaces I care about are obviously U and W. They intersect at something, like, so I should take the basis of U intersect W, call that like V1 to VA. I could extend it to a basis of U by like U1 to UB. I could extend to a basis of W, W1 until WC. And because this is the intersection, and these are all bases, like, these 2 things are linearly independent. So I can just glue these all together to get a basis of U plus W. And so this is now trivial. This bit is A plus B plus C. This is A plus B. This is A plus C. This is minus A. This is obviously E. And this is a fairly simple example, and I'm sure people have already seen this before, but there are just so many applications of this core idea, and this is incredibly useful. So, another example of where Steinitz is like a really, really useful theorem to bear in mind is anytime we ever want to deal with a function from our vector space. So, for example, a function from B to W. So, the natural subspace to care about when you have a function is the kernel. So, the basis we should always choose starts with the basis of the kernel of this function and then extends it. And this immediately gets you rank nullity. You take a basis of the kernel, V1 to V nullity, you extend it, so you add on W1 until Wn, and then it's pretty clear that this is the basis for the original space. These all go to 0, these go basis of the image, and rank nullity immediately follows. I imagine people have probably seen both of these ideas before, but hopefully this has kind of made my point that Steinitz is about choosing the right basis. The basis that lends space through, and having the right basis can make a lot of things just so much easier. So now I want to kind of return to what I promised earlier. Like, what is this course actually about on a really high level? And what it's all about is a bunch of theorems about how good a basis you can choose in different settings. So, for example, one chapter is about linear maps from V to W, and the fundamental theorem of this chapter is you can choose a basis, so the matrix looks like this. There is just like the identity matrix with a bunch of ones on the diagonal and then zeros everywhere else. And this is an incredibly nice basis because it just takes vectors that look like, say, 1, 2, 3, and then if rank is 2, it sends them to 1, 2, 0. This is just like a really lovely map. It just truncates things or adds zeros on the end. The next bit is and also observe that the way you prove this is just by the idea we had over here. You take the kernel of this function, you can extend that to a basis of the entire space, and stuff followed by just doing a bit of fiddle. Another interesting setting we want to look at are functions from a space to itself, so endomorphisms. And here, stuff is harder because these two spaces have the same basis. So we can't just freely choose an amazing, gorgeous basis and get something like this. And here, the fundamental theorem is what's called Jordan normal form, which says I can choose a basis where my matrix has a bunch of blocks along the diagonal and zeros in between, where a block looks something like this. And chapter 3 is basically entirely about what this actually means and why this is really cool and interesting. So I'm going to leave that there for now. But I hope it's at least clear that this is an interesting basis. The next area of the course, well, not the next area of the course goes, because it's not in order, but another area we really care about are bilinear forms. So these are things that take an input in a vector space V, take an input in another vector space, are linear in both arguments, and give me a real number at the end. And here, the best basis we can choose is, again, something that makes it look like this. Because we can choose a basis of V and choose a basis of W. We have loads of freedom. We can get it looking amazingly gorgeous. One point worth stressing when talking about bilinear forms is that even though these are both matrices, these are fundamentally different objects from these matrices, as is illustrated by the fact that transformation rules look like this, not while the transformation rules up here look like this. No, inverse and transposes are completely different things, and so these transform in completely different ways, and so they're fundamentally different. And so, for example, a common mistake I've heard of some people make in supervisions is doing things like taking eigenvalues and trying to diagonalize a matrix like this, or like putting it in Jordan normal form, and you can't do that because it's a fundamentally different object, which is why I wanted to stress that. For example, if you double every basis element, this shrinks by a factor of 4, this doesn't change. But that's an aside. The main point I want to make is that you can choose a blobby basis where it looks like this. Again, natural specialization. You want to look at the same space on the side. And we also want to look at symmetric things. And here, the fundamental theorem says, is Sylvester's law of inertia. It says you get things like this. I'll talk about this a bit in talk 2, but again, this is just a really nice basis. Also observe, this is completely different to Jordan normal form. Again, they're just fundamentally different objects. And I think, in some sense, these are the 4 most important theorems in this course, because they tell you, every time you every time you have an object like this, 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 or this, you should choose a basis like this, 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 or this. And that is the basis that respects the structure of your problem. And I guarantee you things are just so much nicer when you do this. The next category of interesting bases are ways to take a basis of one space and create a basis of a related space. I think the best example of this are bases of dual spaces. So, in some sense, the fundamental theorem of dual spaces says, given any basis of V, I can send it to a dual basis. I can go from EI to FI, a basis of V dual. And the way to approach all dual space problems ever is to look at the kind of structure on V, like are there maps, are there subspaces, pick a basis that respects that structure using all of these previous ideas, map it to a dual basis, and get something nice out at the end. But I'm going to leave the rest of that for talk 2, where I go into dual spaces in a lot more detail. And another example of kind of choosing a basis of related spaces, which isn't gone into in too much detail in this course, is the space of linear maps. So the set of linear maps between V and W is just another vector space. I can add two linear maps together by adding their outputs. I can scale one by scaling the outputs. This is this is n-dimensional, this is m-dimensional. This is a-dimensional, and this is b-dimensional. Then this is an ab-dimensional space. And the sensible basis to take of the space of linear maps is to say, I pick a lovely basis of V, I pick a lovely basis of W, and then I look at matrices in this basis, and I just take matrices with like a 1 in the ijth position, a 0 everywhere else. Everywhere, 0 is everywhere. And call this the like Aij matrix. And this is the natural basis of the space of linear maps. So that was a lot of ranting about how important bases are. So now I want to do an example of how important bases are, because I don't think I have enough bases yet. So I'm going to take example sheet 1, question 12, and try and argue that it's completely trivial with the mindset of pick the right basis. So this example sheet, sorry to all first in the audience. So this question says, I have 4 vector spaces, A, B, C, and D. I have a fixed linear map from A to B, a fixed linear map from C to D. I then define a linear map between the space of linear maps between B and C and the space of linear maps of A and D by taking one and sticking alpha and beta on either side. So I think at first glance this is like a really weird problem. You've got 4 vectors. Oh, and what is the rank of F? So I think at first glance this is like a really weird problem. Like you've got 4 different vector spaces. You have a linear map between the space of linear maps and another space of linear maps. Like what the hell? Sorry?
Your L should be at the beta.
Oh, thank you. Yep, please do chip in with corrections if I make a mistake at any point. Thank you very much, Michael. Yeah, so like, this is a really weird and abstract and messy problem, and you probably have no idea how to think about it. But from the mindset of what's the correct basis to choose, this is really easy. So what's the structure of this problem? We've got 4 vector spaces. We want to choose a basis of these. We have 2 fixed maps, alpha and beta, between 2 different vector spaces. What is the appropriate fundamental theorem? Linear map between 2 different vector spaces. Choose a basis so it looks like identity followed by zeros everywhere else. So I want alpha to look like this. I want beta to look like this. And that gives me a basis of A, B, C, and D. I now choose a basis of linear map from B to C in terms of this. Matrices with like a 1 in a particular place and zeros everywhere else. I similarly choose a basis of AD. And to avoid getting too notation heavy, I'm going to do the special case of these are all two-dimensional spaces, R and S are 1, but this is going to perfectly generalize. Now my linear map is just, I just need to look at what happens to the basis of this space. And just stick these two matrices on either side. And so like, this is alpha, this is beta, this is theta, what happens? If there's a 1 over here, it goes to 0. If there's a 1 over here, this sends it to 0. If there's a 1 over here, this sends it to 0. And if there's a 1 over here, it stays a 1 over there. So the rank is 1. And in general, you can show that if the 1 is in like column S onwards or row R onwards, it's preserved, otherwise it's sent to 0. So the rank is RS. I kind of skimmed through some details fairly fast there, but the point is just, you've got this really weird abstract problem. You pick a lovely basis using the obvious structure of the question, and it's just really easy. This is just like a straight computation, and you get the rank. And the final really important theorem of this course is the Gram-Schmidt thing. So this is just another theorem about choosing great bases. But this time it's a theorem where we care about inner products. So the Gram-Schmidt theorem, which I think, yes, in vector matrices, so first we've seen it too. This theorem just says, if I have a basis v1 to the n, I can choose another basis, w1 up to wn, so it's orthonormal. Each vector at the same length is unit length, and they're all perpendicular to each other. And the spans of the first k things are the same. So anyone has anything for this notation just means span, like what thing can be written with the sum of these various vectors. And so this theorem pairs beautifully with the Steinitz exchange lemma. You can take a problem where you care about nested subspaces. Like say, I've got a subspace I'm projecting onto. You can use Steinitz to take a basis of that and extend the basis of your entire space, and use Gram-Schmidt to convert it to an orthonormal basis. And the takeaway from Gram-Schmidt is, I would again consider this an intuition problem. It's a way to take a problem with subspace structure you care about and inner products you care about, and choose an orthonormal basis that respects the subspace structure. And this will just make any such problem way easier. And an additional point, when it comes to passing tribotomy by exams, is applied Gram-Schmidt is again a really typical question. And it's first off worth just paying attention. This is a typical question. Practice it, learn how to do it well, and just bash it out in the exam. But there's also a useful trick that I think a lot of people don't do for doing Gram-Schmidt efficiently. So the Gram-Schmidt algorithm is like, you take a basis, you take like W2 equals B2 minus this thing. You like knock off the components for all the other things, and then you like normalize. And the point is, the algorithm is often presented like this. You knock off the various components and normalize, knock off the next component, normalize, etc. I think this is the wrong way to do this algorithm, because at each step you're normalizing. And when you normalize, you kind of get icky square roots everywhere, and the algorithm becomes messy, and it's there. The right way to do it is to skip the normalization step. You just take a basis, and then knock off the components parallel to all the other vectors to get an orthogonal basis. This will still work, because we didn't need the fact that W1 was a unit vector. And then at the end, we normalize everything. And I think that that's like a lot faster and has a lot less messy algorithm. So remember that. Also, if you're doing numerical analysis, it's also really useful there. When you're dealing with orthogonal polynomials. And cool. So that's the end of the kind of really, really high-level intuition chapter. Just to recap the kind of important ideas in there. The reason we care about linear algebra is linearity lets things vary independently. It formalizes fuzzy intuitions about things like degrees of freedom. And you should always think to use it when you have a problem where degrees of freedom are really important. The first step in solving any linear algebra problem ever is choosing the right basis, because bases are a lens of your space theory. And all of the big theorems of this course are about how to choose the right basis in various settings. Whether it's about subspace structure, we should use signets. Whether they're interesting maps, we should use the various theorems. Whether you care about linking one space to another, we should just choose a related basis. Or whether you care about inner product, we should use Schmidt. And the final point is that another reason we really care about linear algebra is that this just is really useful in the real world, well, maths, which is close enough. And the point of studying this is that we kind of build a toolkit of ideas and then see unfamiliar settings and apply our toolkit of ideas. I'm going to maybe take a 30-second breather here, and then we're going to go on to doing some stats. That's what you're supposed to cheer. If this talk is appalling you, now is the perfect time.
It's alright, it's visible if you're paying attention.
Good. Does anyone have any questions about the first chapter before I move on? I'll take that as a no. Sorry? Thank you. Cool. When I said 30-second breather, I actually meant 30-second breather. So, yeah, people who left couldn't deal. So, now we're on to chapter 2. So, my goal for this chapter is to basically reteach all of chapter 3, putting it taught really badly. So, we're going to do linear regression, and we're going to do it well, and I'm going to try and emphasize both why this is a good setting for linear algebra, why kind of a linear algebra mindset makes it a lot clearer, and what lessons we can learn from this for just understanding linear algebra better. So first off, and for the people who kind of haven't done stats or have no idea what this is about, this is probably going to go quite fast, but I'll try and explain enough that you could follow if you're paying really close attention. So first off, why is stats a remotely appropriate area to look at linear algebra? So I think that the reason that we want linear algebra as like a useful thing to do is that, so normal distributions are like the most important distribution in statistics, basically. And a really natural object to care about is a vector of n independent normal variables. I'm just going to say for now that they have mean 0 and variance 1. So like, I've got n things that look like this. Then the joint probability distribution function of these, so they're independent. So it's just a product of like a bunch of PDFs of normal variables. Looks like some constant I don't care about times the exponential of this. And this should look kind of interesting because this is the length of a vector. If I took the vector of my like n variables, this is telling me that the joint PDF is just a function of the length of this vector. And vector lengths are like great. Vector lengths let me apply linear algebra ideas. So what I could do is take any orthonormal basis, rewrite this vector in terms of that, and then the length just transforms to be the length of kind of the sum of the squares of each new component. For example, if I have two variables, so like f of xy is something times x this thing, and I choose a new basis, 1, 1, 1 minus 1, then I can rewrite x squared plus y squared as x plus y over root 2 all squared plus x minus y over root 2 all squared. Like, I just rewrite this to my new basis. And so I can just get rid of this. And this is now the sum of still the sum of squares. And so I can factor this again. And I get the PDF of x plus y over root 2 corresponding to this bit, and the PDF of x minus y over root 2 corresponding to this bit. So what we've just shown is that these are independent normal variables. So objects like multivariate normal distributions and linear regression, or the crap we're studying in stats, it follows from this like central thing. The way we've defined normal distributions gives us this great thing where the joint PDF has length in it. Length lets us choose an orthonormal basis, and so any vector of independent normal variables in any orthonormal basis gives me some new independent normal variables. And so, and like that's kind of the point of multivariate and normal distributions, and that's why you study them, though I don't believe that was ever pointed out in the stats course. And so let's do an example of kind of how this lens is actually really useful. I, again, have this like vector, and I want to try and figure out what the variance is, or like each of these satisfies some distribution with unknown mean and unknown variance. And I want to try and estimate what the variance is. So, as we've seen in the course, or people may have seen in like S1 A-level, the thing we get out follows a chi-square distribution and looks like this. You take the mean, you add them up, you divide by n minus 1. And so this is the length of the vector. And so this suggests that something linearity is happening. And what's actually happening is that I want to try and calculate the mean, which means I want to take a vector that looks like this. So like just lots and lots of ones. I want to try and get this vector as close as I can to this, and I want to take the length of what's left. And I'm going to call that the variance. I'm not going to get into like why this is a sensible thing to do, but that's exactly what this formula says. This is the length of the vector x minus x bar times just the vector of ones. And let's think about what happens when we do this. So again, this is a linearity problem. And so what's the first step we should take every time? Choose the right basis. What is our problem? Our problem is we have an arbitrary vector, x. We've got a fixed vector, lots of ones, and we want to try and like minimize this length, like find a good estimate for variance. And the way we do that is, this is our subspace, things parallel to this vector. We choose a basis of that subspace, and we extend to a basis of the entire space. And we're dealing with normal distributions, so our basis should always be orthonormal. And so I'm just going to choose, like, make the first element of my basis this thing, call that like vector k, and then I'm just going to choose a bunch of other basis elements so it's orthonormal. I don't really care what they are. The point is just I can do this. And now all I'm doing is I'm writing my original vector x in terms of this new basis. And I've removed the component parallel to this vector because x bar is just like the vector x dotted with k times something. Yeah, sorry, it's this divided by root n. And this is the kind of component in the direction of this vector. And so all we're doing here is I'm writing x in my new basis, call them like y1 until yn. Y1 is the mean, or proportional to the mean. I am subtracting that component off. That's what this means. And I'm taking the length of the resulting vector, which is just the sum of the squares of the rest. And so that's y2 squared, so on until yn squared. This is the sum of independent normal things of the same variance. Because the means of these are all the same, and these vectors are all orthogonal to this, that means the means I get up to these are all 0. That's not a super important point, but you need it. And that tells me the distribution of this, which is what happens when I remove the mean from everything, is just a chi-squared n-1 distribution. I've taken a stats problem, I've converted to linear algebra, I've chosen the right basis, and now the mean is a function of the first component, the variance, or my estimate of the variance, is a function of the last n-1 bits. They're obviously independent, and the distributions are blindingly obvious. It's chi-squared because it's just the length of the vector. Or it's the length of the vector when you remove some of the coordinates. Did that make sense to everyone? If not, please ask a question, because this is like the fundamental motivating example of this entire section. And everything I do from this point forward is just going to be like variance on this core idea. Cool. So, yeah, everything we're going to do from now on is just going to be variance on this core idea of we have a subspace we care about, we take a basis of that, extend, make it more normal, and study what happens. So, and a further note is that the reason we have n-1 here at the end is that we chose the mean from our data. So the mean has 1 degree of freedom, and we removed that, so there are n-1 ways for this to vary. And again, degrees of freedom, the way to formalize this fuzzy intuition is to use linear algebra. The way to make fuzzy linear algebra ideas like clear is to choose a length of your space through basis. And that's all we just did. So hopefully that made my point of the first chapter a little more clear. Okay, so now let's go on to actual linear regression. So the form of the problem is I've got a random vector of n dimensions y. I've got a fixed I know exactly what y is. So y is like known random. N by 1. X is a matrix. It's known, it's fixed, and it's n by p, some other number p. I've got a vector of parameters, beta. So this is unknown, but fixed, and it's p-dimensional. And I add on a vector of error terms, epsilon. So like this is unknown, this is random, and this is n-dimensional. So this is the setup of the problem. I know this vector. I know about a matrix of coefficients, some kind of linear map. I want to try and figure out what beta is, but it's like the best fit to my data. So like one example, which anyone who's on A-level stats will have seen, is I've got a bunch of points in the plane, things that look like xi, yi, and I want to take a straight line that fits this one. The way to formulate this in this form, this is y is the vector, y1 until yn, x is the matrix, x1, 1, x2, 1, until xn 1, and beta is a 2-parameter thing, the gradient of the line and the constant term. X beta is just like mx1 plus c, mx2 plus c, so on. I subtract that off from y, and I want to like try and make the errors as small as possible. I want to find the line that's the best fit for the data. And linear regression is an incredibly useful area of stats. Like, it's everywhere in machine learning. It's everywhere if you're just like doing data science in the real world. Things that are linear are everywhere, because linearity is a really common relationship between things, but it's often a really good approximation to that true relationship. And so this is like a really, really important area of stats to just know well, if you want to do stats in life. So, and we can kind of boil this down to a linear algebra problem, to a pure linear algebra problem by saying, I know y, I know x. What is beta? So that beta is the argument of the length. Meaning, beta is like the thing that makes this length minimized. If you haven't seen the stats before and that lost you a little bit, just think of it as we want to solve this problem. You've got a vector y, you've got a matrix x. What is the vector parameter beta so that the length is minimized? The reason we care about this is that a common way to model this problem is to say that epsilon is a vector of independent normal variables. Y is thus also something like that. And the probability density function of epsilon is like a constant times like another constant times the length of epsilon, which is y minus x beta squared. We want to find the beta so that this outcome is most likely, which means we want the probability of finding exactly the epsilon be as likely as possible. So we want the probability density function to be as big as possible, which means we want the length to be as small as possible, because the smaller the length, the bigger the PDF. And this is now just a linear algebra problem. How do you find beta to minimize this? And this is not that hard a problem. So let's do a simple example. N is 2, P is 1. We take a plane. We take x. X is just a vector, and beta is just a scalar. So that's a line in the plane. And choosing beta is like choosing a point on this line. Y is another point in space. And we want to choose a beta, choose a point on this line, so that the length is as small as possible. And how do we do that? The way we do that is just by dropping a perpendicular and taking the closest thing. This is like how to find things that are as close as possible. And again, this is a linear algebra problem. So how do we study this? We choose a basis. So our basis should be this line. Our basis should be a thing perpendicular to it. We write y in this basis, and then x beta is just like the first coordinate of y, and y minus x beta is just the second coordinate of y. And like this is a really lovely form. So let's do this and check. We can take x is some matrix, like call this like column 1, call this column 2, call this column P, and beta is something. Beta lets me take a linear combination of these columns. And so choosing beta is like choosing a point in the column space of X, the subspace spanned by these vectors. Equivalently, X is a linear map, and I want to choose a point in the image of X. I'm always going to choose X so that it's got rank P, meaning these columns are all linearly independent. That's not an important assumption, but it just means that I don't have to worry about, say, this column being the same as this and not actually having P being there. So the image of X is a subspace. I'm going to call that U. And that's a subspace of V, the n-dimensional space where Y lives. What do I do to this problem? I take a basis of U, I extend to a basis of V, I use Grommer-Schmitz to make them orthonormal, and this problem is now really easy. I write Y in my U basis, so Y1 until Yn. It's orthonormal, so these are still independent normal variables, where the mean is just, you take the original means and you kind of put it in the new basis, and the variances are all the same. They're still sigma squared. And now, x beta, so x in this new basis, looks like some P by P matrix followed by zeros. P by P n minus P. Because the first P elements of my basis span the columns. Note that I can't just choose the columns because I need an orthogonal basis, and the columns aren't necessarily orthogonal to each other. And beta is just like a random p-dimensional thing. So x beta looks like a beta followed by a bunch of zeros. So the first p coordinates can be chosen freely because A is an invertible matrix, it's square, and the columns are linearly independent. So choosing beta is the same as choosing A beta because it's invertible now. So I want to choose a vector with p numbers followed by n minus p zeros that's as good a fit to y as possible. How should I do that? The obvious way to do it is to just make these coordinates, the first p coordinates of y, I don't care about these because they all have to be 0. A is invertible, so I can always do this. And that is beta. Beta is, beta is A inverse times y1 into y2. We have just derived, or this is an estimated of beta. We've just derived like maximum likelihood estimator of beta. You've probably seen this in an alternate form. You would have seen it as something that looks like this. I believe. Is that the right way around? Excellent. I'm going to pass my exams. And let's see how this kind of trivially goes to this form. This is the truncation of y. This is a linear map. Q with like a 1. This is like an n. Sorry. The map, like, remove the last n minus p things, is a p by n matrix where the first block is of the identity, the rest is zeros. So this is saying beta hat is A inverse Q times Y. Q transpose is another interesting map. It's the matrix that looks like this. So the identity for my zeros on the end. This is the pad by zeros map. And X is just an invertible matrix followed by a pun of zeros. So this is an invertible matrix followed by padding by zeros. So X is A followed by Q transpose. And so now we can just like rewrite this all in terms of A's and Q's and try and get this all in terms of X. And this formula just completely falls out. Beta hat is A inverse QY. This is A inverse A transpose inverse A transpose QY. This thing is just X transpose. This thing is A transpose A inverse. This is A transpose Q trans, A transpose Q transpose A inverse, because if you like pad by zeros and remove zeros, that just does nothing. And this is X transpose X inverse. And that's the formula. For exam-related tip, if you ever need to rewrite this formula, just remember that in the case n equals p, you can exactly choose beta so that x beta equals y, in which case you can just invert this as x inverse, x transpose inverse, x transpose y, these cancel, and just x inverse y. So x beta equals y. So if you're ever like sanity checking, you're like, what are the orders, how does it work? Just apply this and you'll figure out who screwed up. So, okay, so now let's try and think about what the consequences of all of this like linear algebra formulation was. Linear regression was fundamentally about kind of taking a subspace, the image of x, projecting y onto that subspace orthogonally, taking that like bit you've created and subtracting it. So another object we care about in this chapter are what's called the residual sums of squares, which are just like the length of the remaining vector. The reason we care about this is if you look at this is just the length of epsilon. We want to choose the maximum likelihood estimator, which means the thing that makes epsilon as likely as possible. The PDF of epsilon is constant times x constant times length epsilon. So you want the length of epsilon to be as small as possible. And this thing is like a really good estimator for what the variance is. So this is kind of like a constant times our best guess of what the variance of the error terms are. And the distribution of this is really easy because y is a vector. Beta hat speaks of these bits, and y minus x beta removes these bits. So the length of y minus x beta is the sum of the squares of these bits. So the residual sum of squares is the sum of the squares of n minus p things. These are all normal variables at mean zero for boring infinity reasons, and they're all independent, and they all have variance sigma squared. So the distribution is sigma squared n minus p chi squared. And it's independent from beta hat because we're in an orthonormal basis, so all of these are independent. Beta hat is a function of these bits. Sigma squared hat is a function of these bits. And if you've got two functions of completely different independent variables, that output's obviously independent. There's no possible relation there. And there's some ungodly theorem in the middle of the course where you like prove this by some crap about matrices and projection maps and 2n by 2n matrices. This is all that's going on. We choose the right basis, and it's trivial. Another result. And also observe that everything we've just done is just kind of a generalized version of the first example I ever did. The first example I did in the chapter. Calculating the variance as the sum of xi minus x bar all squared. Because that was just the case when x is the vector of all ones, beta is just a single scale. So another result we care about is the Gauss-Markov theorem. The Gauss-Markov theorem says that beta hat is as good as good a linear estimator as you can get of the actual beta, which is phrased as if beta squiggle is another linear unbiased estimator, then the variance of this is estimated the variance of that. The details aren't important. The point is just, this is a way of phrasing, this is the best possible estimator. Any other estimators are just a bit crap. And the reason that happens is, this is linear, so it's a linear map of 1. Beta hat uses only these bits, none of these bits, and these bits contain all the information about beta, and it uses them linearly in kind of exactly the way it needs to. So you can't do anything better. The only way to have a different matrix that's still unbiased is if it does something with this garbage noise. And if you look at the proof of the Gauss-Markov theorem, it says beta squiggle is a linear map of y, beta hat is also a linear map of y. In the right basis, A just takes. A just deals with this bit. This is a different matrix proportion. D just accesses these elements. C accesses these elements and maybe more. And if you write C as D plus another thing, then this bit is only engaging with garbage noise. And the Gauss-Markov theorem is basically just a really messy, convoluted way of showing this extra bit handles garbage noise and provides nothing other than adding variance. So, and the final interesting example here is hypothesis testing. So the natural setting of hypothesis testing when dealing with objects like this is, I think there's some great linear model x, where x are my parameters, maybe x has too many variables in it. There's one column that does nothing. So maybe I can remove a column. So the null hypothesis is the null hypothesis says I don't need that column. The ultimate hypothesis says I have the column I care. Sorry, that was backwards. You might say, I've got a linear model. Could I add an extra parameter? Would that be useful? That would be the ultimate hypothesis. So the null hypothesis says, I've got a stripped down map x naught, let's say one column. The ultimate hypothesis is, I've got a new map with a new shiny parameter. Does this add any value? I'd call the matrix x. It's got more columns. X naught is an n by p0 matrix. X is an n by p matrix. And the question is, does adding these extra columns do anything? For example, I'm doing linear regression, and I've got a line through the origin, and I'm like, what if I translate? Could that add anything? So in that case, x naught would be the vector of just like points, and I multiply by the gradients, but I have no constant number that goes to the origin. And x is these bits. So, and the key point here is that the columns of x naught are a subspace, span a subspace of the columns of x, because I'm just adding more parameters to my linear model. You could get examples like analysis of variation where it's slightly different, and this column gets split up into different bits, but like that's not important. And now we want a hypothesis test. So we want to say, does adding in these extra columns kind of notably decrease the error? So there are two interesting things I can find. The residual sum of squares for like the null hypothesis, and the residual sum of squares for the ultimate hypothesis, where I just like choose beta naught hat and beta hat as I did in the previous case. And this kind of represents the size of the errors in the ultimate hypothesis. This represents the size of the errors in the null hypothesis. And I want to see, has the size of error gone down noticeably when I went to the ultimate hypothesis? So I want to choose some test statistic that bigger, the more useful the ultimate hypothesis was. That's all hypothesis testing is about. And the way to do this is you take the kind of size with the null hypothesis minus the size with the ultimate one, like the kind of added bits, or the bits that got removed. You divide by the kind of size of the ultimate hypothesis. And if it's pretty clear that the more useful the ultimate hypothesis is, the bigger this is. So this is our test statistic. And what's the distribution of this? This is projecting onto a subspace. This is projecting onto a bigger subspace of that, which is still a subspace of the entire space. And so we pick a basis of x naught, extend to a basis of x, extend to a basis of the entire space, make it all orthonormal. We write y in that basis. And the residual sum, the null residual sum of squares is the length of this bit. The residual sum of squares is the length of this bit. The difference is the length of this bit. So they're obviously independent because they're just the sum of squares of different bits of my vector. And the distribution, the number of degrees of freedom, has been beautifully phrased by choosing the right basis. Because linear algebra at its heart is all about choosing the right number of degrees of freedom. Kind of giving me a way to think about degrees of freedom. And that's all that is going on in this chapter of stats. Are there any questions about that? Cool. This represents a very natural, definitely halfway point in my talk. So I'm going to take a 2-minute break here, and then I'm going to start talking about endomorphisms. Apologies in advance when this inevitably massively overruns. I will not be offended if anyone leaves at 10. Leaves at half.
Halfway through this class?
Sorry?
Halfway through this class?
Halfway through this. Well, I mean, not actually half. Because it's like a natural break.
Okay, no,
I'm not going to go on until 10. That's okay. I'm not going to go on much past 10. Worst case scenario. Sorry?
Your first number,
Okay. People ready to begin again? Cool. Just to ask again, does anyone have any questions about the first part? Cool. So now I'm going to get on to kind of like an actual bit of the course. So studying endomorphisms. And endomorphisms are a linear map from a space to itself. And we want to like study these, and our central goal is to find as lovely a basis as possible. And so the kind of classic example of incredibly nice linear maps from a vector space to itself are diagonal matrices, things that look like this. So the reason this is so nice is that it just scales each basis vector and it doesn't move them between each other. So the way to understand a diagonal matrix is just look at each basis vector. And for example, this is really easy to invert because I just say on each basis vector it scales. So to invert that on the basis vector, I just divide by that amount. And so I just write 1, a half, a quarter. And that's the inverse. And so the kind of dream we're going to have is I want to make every single matrix. I want to find a basis for every matrix where it looks like this. Unfortunately, as with reality, our dreams are not going to actually happen. And it is not the case that every matrix has a basis like this. We can get really close. So first I want to think a bit more about what it actually means to be taking a basis like that. So my motivating example is going to be this matrix, 1, 1, 1. If I input a vector xy, it gets sent to x plus y, x plus y. So like, this is a scalar multiple of the vector 1, 1. So if I look at the plane, everything gets projected onto this line. So what's happening here is I can choose a really nice basis, 1, 1, and 1 minus 1, where this vector is sent to 0, and this vector is sent to twice itself. So this is an eigenbasis. And what I've actually just done is I've taken my space, I've taken 2 subspaces, these 2 lines, and I've decomposed the space into those. My linear map sends each one to itself. It sends this line to itself by doubling it. It sends this line to itself by sending it all to the origin, which is still on the line. And these are called invariant subspaces. Again, an invariant subspace is a subspace where my linear map sends it to itself. And this is an example of like a decomposition I did. And decompositions are one of the most kind of fundamental high-level ideas of maths. You take something complicated and you break it down into small bits, where you can understand each individually and independent of the rest. And then you can build this back up to an understanding of the entire space. And you should kind of get really excited whenever you see anything like this, because, for example, in number theory, the fundamental idea of decomposition is prime factorization. You can take any number and break it down into bits where you can't divide any primes. And imagine doing number theory without primes. I would assert that studying endomorphisms without thinking about invariant subspaces is like doing number theory without thinking about primes. So the entire rest of the chapter is going to be about how great they are. for example, the matrix, if I choose a basis of a bunch of invariant subspaces, which kind of sums my entire space, then the resulting matrix is going to look like a block for like each invariant subspace and zeros in between, because the basis vectors here are sent to other basis vectors here, so there are like zeros. Basis vectors here sent to basis vectors here, there are zeros. There's no kind of bits that go between, because if there were, they wouldn't be invariant subspaces. So, for example, if you do representation theory in third year, this is just like the entire course is about looking at stuff like this. And what my dream is going to be is to say, for every vector space, I can break it down into invariant subspaces, where the map is much nicer on that invariant subspace than was on the entire space. I'm going to want to break it down into things that can't be broken down further, and somehow leverage the fact that can't be broken down further into having a good understanding of what the space looks like. In the same way that when I study prime numbers, the fact that they have no factors gives me a massive in to understanding them better. So, and just so you kind of have an idea of where we're going, I'm only going to look at vector spaces over the complex numbers for reasons that will become clear later on. And every matrix has what's called Jordan normal form, which means there's a basis, so there's a bunch of blocks, like J, M, lambda, zeros everywhere in between, and a block, J, M, lambda, is a matrix that has lambdas on the diagonal, ones above the diagonal, and zeros everywhere else. So this doesn't seem anywhere near as nice as the glorious dreams of diagonal matrices earlier. Like, this isn't scaling, this is like some ungodly weird math. But this is actually a really nice math. The reason it's so nice is you can write it as the lambdas with zeros plus the ones. Call this lambda I, call this j. And so lambda I, we understand. J seems a bit weird. What does it mean to have ones just above the diagonal, zeros everywhere else? This is a linear map that takes a vector, x1 to xm, and sends it to the vector x2 until xn followed by 0. It like shifts it up by 1, and it kills the final coordinate. And what happens if we apply this twice? We shift up again. This goes to x3 until xm, followed by 0, 0. And we keep doing this. So J is an example of a nilpotent map, which means when you apply it m times, you get the 0 map. And that's why this form is so nice. We've broken down our vector space into invariant subspaces, and on each invariant subspace, it looks like scaling plus a nilpotent thingy. And so to give one example of why nilpotent things are really nice, let's think about what happens when we take our matrix to a massive power. So let's take a specific example. The size of the Jordan block is 2. So I have lambda I plus j, where j is this matrix. What happens when I raise this to the power of 1,000? So I'm use the binomial theorem because j commutes with everything in here, so I can expand this, and I get a bunch of powers of j. And I'm going to get bored and stop writing here. The reason I've got bored is that every other thing is j squared, j cubed, j4, etc., and so they're all 0. Which means that this map is just this bit. So as a matrix, it looks like lambda to 1,000 times 1,000, lambda to 9. And so this is a really nice map. And there are loads of problems where this form and this basis just makes it a lot cooler and a lot easier to work with. For example, let's say an inverse. Now I'm going to be even more adventurous. Rather than using a finite, boring binomial theorem, I'm going to use an infinite power series. So I can write this as 1 over lambda times I minus j of lambda, power of minus 1. I'm writing it like this so it's in the form 1 over 1 minus x. The power series of that is x plus x squared plus x cubed, etc. So this is 1 over lambda times minus k over lambda plus minus k over lambda squared. And, I plus. But all of these terms in this infinite power series vanish. So first off, as long as lambda is non-zero, this has an inverse. And secondly, the inverse is really nice. The inverse looks like 1 over lambda minus 1 over lambda squared. And this was an n equals 2 example, but this same logic works for any Jordan block. You just have more terms. And hopefully I convince you that this is a kind of great goal to be working towards. So now I'm going to try and actually get into the guts of the maths and how we actually go about breaking these things down. I think this is the hardest bit of the talk, so if I lose some of you, I'll try and signpost kind of what you need to understand and which bits and where you can start paying attention again. And please do ask questions if I say anything and it's kind of confusing, it doesn't make sense. So, first off, Jordan normal form, the kind of final bit of every block is an eigenvector, which suggests that looking at eigenspaces and eigenstuff is a good idea. So, question 1, what is an eigenspace? How do we actually define it? I think that the right way to define eigenspaces is as the kernel of my linear map minus the linear map of a scale. So I'm going to call this the lambda eigenspace of A. The reason I think this is a great definition and much easier to work with is that kind of kernels are intrinsic properties of the linear map, and they're really easy to manipulate. For example, let's say I want to look at the eigenvalues of A squared. This is going to be the kernel of A squared minus lambda I. This is complex numbers, so lambda is mu squared. So this is, and so this factorizes into A minus mu I times A plus mu I. And if a vector is sent to 0 by one of these, then, if the vector is sent to 0 by this, like I said, the kernel, then it's either sent to 0 by this bit, or this bit does something to it, and this bit sent it to 0. And because these two things commute, the second case is just saying this sent the original vector to 0. So the eigenspace of A squared is stuff where AB is mu, and stuff where AB, or stuff where AB is minus mu. So eigenvectors of a map squared are always eigenvectors of the original map, where the eigenvalue is kind of exactly what you expect it to be. And hopefully this made my point that this is the right way to think about eigenspaces and eigenstuff. Because, and further observe that the fact that we were in C was really useful there, because we had a polynomial, and we factor it into linear bits. And ultimately, eigenstuff is all about kind of linear factors of my linear map. And because they're all about the place of my map is the same as scale. And the reason we care about being in C and being in an algebraically closed field is so that I can take any polynomial and convert it to lots of linear bits. And now I'm going to use this idea to show that every linear map has at least one eigenvector. This is probably not going to be a proof we've seen before. I don't think it's the proof in the course, at least. So, theorem. Every map from a vector space to itself has an eigenvalue. So the reason this is true is I can pick any non-zero vector, W. I can look at a W, E squared W. I get an infinite sequence until A to the n W. I now have n plus 1 vectors in an n-dimensional space. And so they are linearly dependent. There is some linear combination of this that's non-trivial, that is 0. For example, let's say it's a squared W minus plus 2AW plus w equals 0, e.g. This is a polynomial of a. And this factors, because we're in the complex numbers. No matter what the polynomial was, it would factor. And each linear factor is just a linear map, and we're just composing all of them. And at the end, we've gone from a non-zero thing to a zero, which means at some point in the process, like say I had the linear map a minus I, a minus 2i, a minus 3i, of w equals 0, then w is non-zero over here, something over here, something over here, 0 over here. There is a point where it goes from non-zero to 0. So one of these maps has a non-trivial kernel. It sends something to 0. And so one of these maps has, this is an eigenvector of one of these maps. Sorry, not that this is an eigenvector of one of these maps, but at some point there is an eigenvector of one of these maps, which means every linear map has an eigenvector. I really like this proof. And was that clear to everyone? Cool. So one thing to point out here is that I have very, very deliberately not given the standard proof. So the standard proof would be like, you look at det a minus ti, this is a polynomial, it has a root. At that root, this has zero determinant, and so when it has zero determinant, it's non-invertible, so it says something to 0, that's an eigenvector. I really don't like this proof, because it seems simple, but it's actually hiding a really complicated and sophisticated thing in the box called determinant, because determinants are hard. And I really hate the perspective of linear algebra, where you define determinants first thing as this messy sum of permutations, and they argue it to volume, and you have no idea what the hell is going on. And you use it in these really important proofs, and it feels really fundamental, and you leave the course just having no idea what's going on. I think linear algebra is a little bit better, because they look at volume forms, but this is still quite unsatisfying. And so I'm going to leave determinants to the end of this chapter. And I'm going to try and give a definition which actually makes sense and where it's intuitive as to why it means volume. And so it's important that I haven't used determinants at any point thus far, because I'm going to use all the theory to define them, because they're a hard object, and you build theory to understand hard things. So, okay. So it's not the case that every linear map has an eigenbasis. For example, this linear map doesn't have an eigenbasis. It's set, the only eigenvector is 0, or multiples of 0. But if we instead look at, or look at this, the only eigenvector again is 0, 1. But if we instead look at the map squared, it's 0, which suggests that we can still do something clever to figure out our invariant subspaces from this map. So let's try and be creative and figure out how to generate invariant subspaces. We're dealing with a linear map, and so the natural subspace to care about are the kernel and the edge. And it's kind of obvious that these are both invariant, because the kernel is the things that get set to 0. So when you apply A, you just get 0. It's obviously in there. If you apply A to anything in the image, you get something in the image of A squared, which is obviously in the image of A. Like when you apply A, you get something in the image. So these are both invariant. And even better, by rank nullity, their dimensions add up to n. So now at the point we should get really excited, because we've got two invariant subspaces whose dimensions add up to n. But we're not done, because they could overlap. For example, in this case, the kernel is things of this form, and the image are things of this form. This is sad, they overlap. But if we instead looked at the kernel of A squared and the image of A squared, all the logic I just said still works. This is A invariant, this is A invariant. Their dimensions add up to n. But now, this kernel is xy, this kernel is 0, 0. They're disjoint. And it turns out that this clever idea will work in general. I can take any linear map, write the kernel of like a to the k for some k, the image of a to the k for some k, and together they will be a decomposition into invariant subspaces. So let's do this. What actually happens when we try and follow through this clever idea and look at these spaces? So as I said earlier, the image of A squared is a subspace of the image of A, because when you apply A to a thing in the image of A, you also get something in the image of A. And MA cubed is a subspace of the image of A squared, etc. And the kernels start at 0 and go upwards, because if A squared is equal to 0, then if A is equal to 0, obviously A squared also set it to 0. And if A squared is equal to 0, obviously A cubed set it to 0, etc. So these are nested subspaces. This goes down, this goes up. And what's also clear is that the dimensions are decreasing, but they can't decrease forever because they're all between 0 and n, and they're all integers. So there is some k where like image of a to the k has the same dimension as the image of a to the k plus 1. So like there exists a k so that this is true. And I can get rid of the dimensions because they're nested subspaces. And if you have a subspace other than the same dimension, they're just the same space. And so this means that, and this is just what happens when you apply A to the image of A to the k. So this is really, really cool. This tells me that I start with this subspace, I apply A, and I get exactly the same subspace back. A restricted to this is an isomorphism. Because we know that any map that is surjective and between spaces of the same dimension is an isomorphism, core theorem from earlier. And this means that it's not immediately obvious that this means that the kernel of A to the k doesn't overlap. But it actually does imply that, because A is invertible. So we can apply A as many times as we like, and it's still invertible. So let's apply it k times. So A to the k is invertible in here, which means it can't overlap with the kernel of A to the k at all. And now we have our dream. We have two spaces, image of A to the k and kernel of A to the k. Their dimensions add up to n. They're both A invariant, and they're disjoint. Has that made sense to everyone? Please ask a question if I can clarify on that. Yeah?
Can you repeat why they're disjoint?
Sure. So A is an isomorphism on the image of A to the k. Is that clear? So A applied as many times as you like is still an isomorphism. So A applied k times is an isomorphism, which means A to the k cannot send anything in here to 0, which means it doesn't overlap with the kernel at all. So they're disjoint. And it should further be kind of clear that this is really related to Jordan normal form, because if I have a Jordan block like this, with say it's three-dimensional, then this is the kind of icky pathological case. And if we look at the images and kernels, the image of A is like x, y, 0, then the image is x, 0, 0, and then the image is 0, 0, 0. The kernels are x, y, x, 0, 0, x, y, 0, x, y, z. So here, k is 3. 3 is the point where these become disjoint things that we can add together to get the entire space. And we can always do this. So, okay, hopefully I convinced you that this is a true theorem. Why is this an interesting theorem? It's an interesting theorem because, so, let's think about what happens when we actually apply this to specific maps. Because this works for any map, right? If A is the identity, this is really boring. It tells me the identity is an isomorphism, so it has trivial kernel, so V is in A to k, this kernel is k, just V plus nothing. And I know this tells me nothing about the space, it's just the image of something. But if we take another standard map, like the 0 map, then now the image is 0, and the kernel is V. And this actually is something quite weird, because this tells me that the entire space is set to 0 by 0. And that's like a really strong condition. It tells me it's the 0. So this kind of motivates the idea that the way to use this lemma is by finding maps which have a non-trivial kernel, because then this bit is bigger. And knowing that things are set to 0 by a map is super useful. And now we glue our two theorems together. Every linear map has an eigenvector, which means that for every linear map, I can subtract some lambda I so that it has a non-trivial kernel. And now I apply my theorem to B equals A minus lambda I. So, sanity check. I'm going to find B invariant subspaces. Does that matter? No, it doesn't, because if BV is inside my space, BV minus lambda B is inside my subspace, so is BV minus lambda B. Because if I start with a vector inside here, a scalar multiple of that is still inside here. And so the difference between the two vectors inside there is also inside there. Does that make sense to people? We can subtract a scaling map easily, because that doesn't affect invariance. And now I can apply my theorem, and I get that every linear map has an eigenvalue, so I can write it like this. The vector space decomposes into this, the sum value. This has dimension at least 1, and this is like an interesting space. So we're going to like store this to the side and just like keep this for later. And this is the image. This is just like a leftover invariant subspace. And I can look at my linear map sends this space to itself. So I can just look at my linear map from, so I call this W, A from W to W, like restriction. And then this is, I can repeat exactly the same analysis. I can take W, A has an eigenvalue because all linear maps have eigenvalues. And because all linear maps have eigenvalues, I can subtract something off and get another kernel of A minus mu I to the like K2 plus like a leftover bit. And I can just keep doing this until I run out of space. It's finite dimensional, so I'll always run out of space. And so I've taken my B, and I've just broken it down into these objects. These are called generalized eigenspaces. And these are like really cool objects, because on these, A is a nilpotent map. And as we saw earlier, nilpotent maps are cool. And we now kind of done all of the interesting work of proving Jordan normal form. The next stage is to look at a particular subspace. Say, I'm just going to assume that the eigenvalue is 0 because it doesn't really matter. I'm going to look at a space, say, ker A cubed. I want to show that I can choose a basis which gets into Jordan blocks. Note that this could be more than one Jordan block. If I have a matrix that looks like, say, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, just like a bunch of zeros and the rest, these all live inside the kernel of A cubed. So something like, we're going to have to use something more intelligent. And it turns out that the key idea, I'm not actually going to go into details, because I don't think this proof is interesting, it's just quite fiddly. The key is that the end of every block lives in the kernel of A. The second thing in every block lives inside the kernel of A squared, but not the kernel of A. So they're the kind of new bits we add. And the third bit of each block lives in the kernel of A cubed, but not the kernel of A squared. And so the way to derive all this is to take a basis of kind of A cubed, the bits of A cubed that aren't in A squared. Then do the same thing for here and kind of extend. And you can do this in such a way that you get these blocks. As was probably clear from how that was a bit of a mess, this is like messy, and I'm not going to do it. But please take it on faith that this is a thing you can do. And I can recommend sources if anyone really wants to see the proof for themselves. And the cool consequence of the detail I just skipped is that the number of blocks of size k, of size at least k, is the number of, same with the number of blocks which have like a k thing from the bottom. And the number of k things from the bottom is the number of things in the kernel of a to the k that aren't in the kernel of a to the k minus 1. The things that take exactly k steps to be sent to 0. And so this is and so we got uniqueness for free. This is purely a property of my map in the abstract. This is exactly what I need to reconstruct the blocks, because like if I gave you the number of blocks of like size 1, 2, 3, 4, and 5, etc., you could easily give me the number of blocks of size at least of that, and vice versa. And so Jordan normal form exists, it's unique, and it all follows from this like core idea of hunting for invariant subspaces and a few clever magical ideas. So to take one example of why this mindset of thinking about Jordan normal form is useful, let's find the Jordan normal form of the transpose of the matrix. So the key to finding Jordan normal form is looking at kernels of A minus an eigenvalue to some power, and look at the dimension of that. So to find the Jordan normal form of the transpose, I want to figure out what this kind of thing is. And A minus lambda I, A transpose minus lambda I, or A conjugate minus lambda I, is equal to this. And the kernel of the matrix is the same as the kernel of its conjugate. And conjugates can equal like taking it to the power of R. So I can just forget about this. So studying the Jordan normal form of the conjugate of A is the same as studying the Jordan normal form of A, but where you rather than look at eigenvalues of lambda, you look at the eigenvalues of lambda conjugate. And so, what's the Jordan normal form? All of the dimensions of kernels of powers is like exactly the same, but lambda goes to lambda bar. And so the Jordan blocks are all preserved, but they go from this to this. And that's the Jordan normal form of the conjugate. What's the Jordan normal form of the inverse? That would be so again, how do we manipulate this? This is A minus lambda inverse I all to the power of minus 1. Sorry. 1. And this is, and like, we can just kind of ignore the minus 1 bit. And all of the kernels of this stuff are just, they've got the same dimensions as the previous bits, but here the lambdas go to 1 over. And so that gives us the Jordan normal form of the inverse. So, yeah, just to kind of recap everything we just did, the key idea was we started with invariant subspaces, was we want to look for invariant subspaces. This is a really fundamental idea because it's an idea about decomposition. Take something complicated, break it down to simple things. Our dream was to understand a vector space by looking at simple things, understanding those deeply, and building an understanding of the entire space. And we just did all that. We looked at eigenstuff. We discovered this idea of generalized eigenspaces. And from that, with a little bit of the magic I cut out, we got Jordan normal form. And the reason Jordan normal form is nice is it looks like scaling plus something that's more potent. So this is the time I was supposed to end, but I've got a short section which is just like why Jordan normal form is interesting. So if anyone wants to go, feel free. But like really cool stuff's about to happen, so don't. And this is not going to take that long. I promise, this is nowhere as long as the previous bits. This was definitely not planned, just saying. Definitely didn't put all the caution at the end so people wouldn't leave early. So, I've emphasized a few times that theorems about choosing a nice basis are like really fundamental to understanding linear algebra. So, I'm just going to ramble for a while about how amazingly cool Jordan normal form is and how much it helps us understand this space. How much it helps us understand like everything we care about when it comes to endomorphisms. So, and again, the key idea is you've got invariant subspaces, you split into these simple bits, you think about each one independently, and you can build up an understanding of each bit into an understanding of the entire space. So, example 1, minimal polynomials. So, I got my space, I break it up into like a bunch of Jordan blocks. And I want to understand the minimal polynomial on V. My linear map restricts to a linear map on each invariant subspace. That's the point of invariant subspaces. And so each one has a minimal polynomial. And to look at the minimal polynomial in the entire space, it clearly must be a multiple of the minimal polynomial on each one of these. Because, for example, the minimal polynomial on here is like a cubed minus a, and on here it's a minus 1, on here it's a, on here it's a plus 1. This makes sense because this map is 0 on the entire space, so it's also 0 on every subspace. And so the minimal polynomial must divide it. But if instead the minimal polynomial is a minus 2, this is not a multiple of a minus 2, and so the map is, this is not 0 on this subspace. So this can't be 0 on the entire space. So the way to understand minimal polynomials is to break down into subspaces, look at the minimal polynomial in each subspace, and take the least common multiple, because that will be the minimal polynomial in the entire space. And what's the minimal polynomial of the kernel of a minus lambda I to the power of r? So the way we chose r is it's the first bit where this kernel stops shrinking. And so this means that a minus lambda I to the r minus 1 has a different kernel, has like a smaller kernel, which means that the minimal polynomial is like x minus lambda to the power of r, or a minus lambda I to the power of r, depending on how you prefer to phrase minimal polynomials. And this is really nice. This is a linear thing to some power. What's the LCM of a bunch of linear things to powers? They're just the maximum number of times you get. They're just the biggest power that appears for each specific linear thing, multiplied across all the linear things. And so if I break down V into, like, say, the kernel of a cubed plus the kernel of a minus I to the 4, and let's say it's just that, then what's minimal polynomial? It's x cubed here, x minus 1 to the 4 here, and this creates a thing for the entire space. And every time you ever think about minimal polynomials, you should be thinking through this lens, because we've taken a messy thing with a bunch of factors and broken it down into bits of each factor. And this is obviously much simpler. And for example, this immediately implies the diagonalization theorem, because this is clearly the easier way to prove that. Because if you start with, if this has distinct linear factors, then each of these has like power at most 1, because they're all like divisors of that. And so we don't have generalized eigenspaces, we only have eigenspaces, so it's diagonalized. So take another one. Let's prove K Hamilton. So K Hamilton says, say my Jordan blocks look like this. Let's just look at this matrix. So here the characteristic polynomial is going to be x minus lambda to the 5, because the sum of the sizes of the Jordan blocks. You take the characteristic polynomial of each block and you multiply them all together. The minimal polynomial is the LCM of all of these, and on each block, the characteristic polynomial is the same as the minimal polynomial. So the product of the characteristic polynomials in each block is the same as the product of the minimal polynomial in each block, which is obviously a multiple of the LCM. So the characteristic polynomial is obviously a multiple of the minimal polynomial, and that's all the Cayley-Hamilton theorem says. And that's why it's valid to take like a linear map and shove it in like this thing, and just like fudge it and say this is the linear map and say this is 0, yay. That's why it works. And consequence 2. We can now define trace. We've gone through all that work without ever using sophisticated objects like determinant and trace. And so the light at the end of the tunnel is we've now built up this really cool theory, which we can use to understand it. So again, decompose into these spaces. On each space, we've got a really nice matrix. And whenever we have a decomposition to subspaces, there's like a block for each subspace and zeros everywhere else. So we obviously want to define trace, so an add between the subspaces, because they're just like partitioning the main diagonal. So we want to define trace of like my linear map on V, and the trace of my linear map on like each space added together. And this is cool. And how do we define trace on like a particular Jordan block? We can just define it as the size of the block times the number of times the eigenvalue, right? That's obviously how you should define trace on a matrix that looks like this. It's going to be 3 lambda. And so, how do we define trace in general? We can define trace as the sum of the eigenvalues counting by algebraic multiplicity. So like every point they appear on the diagonal, we count that once. And I think this is a much better definition of trace than the diagonal one, because it's obviously basis free. Jordan normal form was a process by which we chose a basis which was intrinsic to our linear map, the basis where it's as nice as possible. And we define this in terms of that basis. And we know that's a unique basis. This is like obviously well defined, and it's obviously basis free. And it's also quite clear that this is the same as the other definition, the like sum of diagonal elements, because that's true for Jordan normal form. And it's not hard to see to prove that this is invariant when you change basis. And so this definition is going to coincide in Jordan normal form, and so they must be the same thing. But I think it's much, much more natural to define something intrinsic to your map, define this weird thing and observe that it's the same, just a computational hack, rather than trying to go the other way around. So sadly, I don't have a great intuitive geometric explanation for why trace is like this and why that is an interesting object to study. But fortunately, I do for determinants. So, and this is the final point of the talk for people who are considering it. So, determinants. How do we define determinant? We should define determinant as the product of the determinant on each subspace, because they partition the matrix and there is zeros everywhere else. And so our definition of determinant takes the thing here, the thing here, the thing here, and multiplies them all together. And what should the determinant of a matrix like this be? We should obviously define it as lambda cubed, the eigenvalue to the power of the size. So how should we define determinant in general? We should define it as the product of the eigenvalues, or the product of the eigenvalues to the power of algebraic multiplicity, depending on how you want to count it. Whether you like just go through every element or you go through every Jordan block, it's just the same thing. And so, again, this is basis independent. We've derived this by looking at invariant subspaces because that's fundamental to how to do linear algebra. And this is intrinsic to our linear map. And again, if we define the kind of ridiculous sum over all permutations definition or Laplace's form of the determinant or any crap like that, it's not that hard to see that it coincides. You can show that the magic formula is invariant when you change a basis. And Jordan form gives us a basis where that's what the magic formula gives us. But there's also a really cool geometric intuition for why this is evolving. Like you've got this basis independent thing, but why does it satisfy all this other lollyhut determinant does? It's because, thinking geometrically, a basis is just a set of axes, and geometrical form is all about picking a set of axes where my map works really nicely. For example, if I have a diagonalizable matrix, I get to choose a set of axes where this is kept the same, this is doubled, and this is tripled. So what happens to the volume of the shape? It scales by 1 in this way, 2 in this way, 3 in this way. You multiply them all together, and you get 6. That's the volume scaling factor. And the product of eigenvalues. What happens when you have a joint block and you've got a shape, like I've got 1, 1, 0? Then my shape goes from this to this. But shears don't affect area. They're like translating parallel to things we don't care about. And so the same logic holds. The kind of interesting scaling along this in this direction is still the eigenvalue. And that's why determinant gives us an intuitive notion of volume. Because determinant is the product of eigenvalues. We can choose a set of axes where the kind of change in that direction is just scaling by the eigenvalue. And the scaling factor of volume is the scaling in each of my n independent directions. And so just to recap everything we've done in this chapter, we broke things down to invariant subspaces. Joule form is a truly fundamental theorem because it gives us a lovely decomposition and it gives us a great basis to think about things in. And this is like the way to understand complicated high-level ideas about endomorphisms, like trace, determinant, minimal polynomial. Because you've broken and complicated things down into simple bits. And so our kind of local simple understanding has been pulled together to give us a glorious global understanding. And that is the end of my talk. Are there any questions? Cool. In that case, thank you very much for coming. If you have any questions, you're very welcome to come to me now and ask. And I would really appreciate anyone who has any thoughts on that whatsoever, or any things they want to see in the next talk, or things like to improve or anything like that, would like message me about them or fill out my feedback form. And I'd also just love to hear if people enjoyed that and what they feel helpful, so I know what things to include more in the next talk. And again, the second part of this talk is at 7:30 in here on Monday. I'm also giving a group strength and modules talk in here on Friday in a week and a bit's time, starting at 8 p.m. And hopefully many of you there, if this hasn't put you off listening to me monologue forever.